Welcome to the video lecture on infinite limits. We are going to take a look at the function f of x equals 3 over the quantity x minus 2 squared. And we're going to explore what the limit of this function is as x gets closer and closer to 2. So I'm going to start by finding this limit numerically using a table of values. And in order to fill out this table as quickly and efficiently as possible, I'm going to use my calculator to help me out. So we're going to use the lists on our calculator to help us do this quickly. So if you go to Stat, we're going to edit our list. So I'm going to click on number 1 for edit. And just to save a little bit of time, in list 1 I already have typed in all of the x values in both of my two tables. And to do that, I just arrowed all the way up to the top of L1, hit enter, and then I just started typing in each x. Now in list 2, I'm going to arrow up to the top so that L2 is highlighted, hit enter so that the cursor is flashing down here at the bottom, and now we're going to type in our function. Now because our x values are actually being stored in list 1, we don't want to use x in our formula down here, we want to use L1 in our formula. So we're going to type in 3 divided by parentheses, and L1 is right here, right above the number 1 key in blue. So we're just going to do second 1 so that we see that L1, and then we're going to do minus 2 quantity squared. And if I hit enter, it will automatically give me all of these values. So if you look at these x values, when x is 1, y is 3. When x is 1.5, y is 12, and look at what's happening to these y values as these x values get closer and closer to 2 from below. So we get 3, 12, 27, 48, 300, 30,000, and 3 million. If I arrow down, this is the list in the second table. So these are values of x now approaching 2, but this time from above or from the right side, so slightly bigger than 2. So as I get closer to 2, let's look at what these y's are doing. 3, 12, 27, 48, 300, 30,000, 3 million. Okay? So you can see that as I get closer to 2 for the x's, the y's are getting larger and larger and larger. So let's take a look at what that means. So if we pull up our chart and just type in those or write in those numbers that we were just looking at, 3, 12, 27, 48, 300, 30,000, and 3 million. And it was the same for these other y values coming from above 2. So if we take a look at our graph, let's see what this translates into in terms of our graph. So when x was 1, y was 3, so something pretty small. When x was 1.5, we were up to 12. When x was 1 2/3, we were all the way up here at 27. When x was 1 3/4, we were up past 48, and so on. So you can see that these are going to start shooting upwards just like that. And likewise on the other side as well. So here's what my graph looks like. Now let's formalize what this means about our limit. So as x goes to 2, what is this function doing? Well, from the left side, we're shooting up towards positive infinity, and also from the right side as well. Now technically that is a limit that does not exist, but to be a little bit more descriptive, we can say that this limit is positive infinity. That doesn't mean it actually exists, it just tells us what behavior this function is taking on. So let's formalize this definition of what we are just talking about. Say that we have a function that is defined at every number in some open interval containing a, except possibly at a itself. As x approaches a, we say that f of x increases without bound, which is written the limit as x approaches a of f of x goes to positive infinity If for any number n greater than 0, however large, there exists a delta greater than 0, such that if x minus a in absolute value is less than delta, then f of x is greater than this n. Now this is referring to that epsilon delta definition of a limit, but the idea, if you look at your graph up here, is you can pick any number n that you want, as large as you possibly want. Say you pick something way up here. Then what this epsilon delta definition guarantees is that if I want my function to be larger than this n, in other words, I want it to be above here, so that would be all of these y values up here, then that forces me to have to be this close to our x value, or our a value. So as long as we can find this delta that's going to get us close enough, we will be able to get our y values to be n or larger. Okay? So now let's take a look at this limit of a very similar function. This time I'm going to put a minus sign on the outside. So we're taking the function f of x equal to negative 3 over x minus 2 quantity squared. And we know that that's just a reflection over the x-axis. So here's my x-axis now. It's up here at the top. And here's my y-axis. So as x approaches 2, we're just going to flip that graph over that we had earlier. So that's going to force it to shoot down like this on either side of 2. And so we would say that the limit as x approaches 2 of f of x, this time because it's shooting downwards, is going to go to minus infinity. And formally we would say that if we have a function f that's defined at every number in some open interval containing a except possibly at a itself, then as x approaches a, we say that f of x decreases without bound, which is written the limit as x approaches a of f of x equals minus infinity, if for any number n less than 0, so any large negative number, there has to exist a delta greater than 0 such that the absolute value of x minus a has to be less than delta, and if that's true, then f of x will be less than n. So you pick any n, then there has to be a delta so that I can get close enough to this a value to force my function's y values to be smaller than n. And as long as I can do that for every choice of n and find a corresponding delta, then this limit will go to minus infinity. So let's find a few examples here. So this time our function is 2x over x plus 1, and this is its graph over here to the right. So let's find the limit as we approach negative 1 from the left-hand side. So here's negative 1. From the left-hand side would mean I'm coming in from this direction, which on my graph would correspond to these y's going up, shooting up. So this is going to positive infinity. And if I'm coming from the right side of negative 1, so I'm talking about these x's, that would correspond to these y's shooting down, so we would say that this limit is going to minus infinity. Now, what does this mean graphically? Well, all of the examples that we've looked at that have had limits going to either positive or negative infinity have had vertical asymptotes on their graphs. And those were the places where that denominator became 0. So we say by definition that the line x equals to a is a vertical asymptote of the graph if at least one of the following statements is true. And what you'll see about all these limits is that they are all going to either positive or negative infinities. So if you have a limit that is approaching a from the right-hand side, from the right over here, and the function is shooting up towards positive infinity, then this line right here, x equals a, would be a vertical asymptote. If you came from the right-hand side of a and instead your graph was shooting down towards negative infinity, we would still classify this line x equals a as a vertical asymptote. If we come from the left side of a and the graph shoots up, or if we come from the left side of a and the graph shoots down, then that's a vertical asymptote at x equals a. And finally, if we come from both sides of a and the graph is shooting down on both sides, or if the graph is shooting up on both sides of a, then that means this line x equals to a is a vertical asymptote. So in other words, you can have a one-sided limit that goes to positive and negative infinity, or a two-sided limit that goes to positive or negative infinity. In either case, you have a vertical asymptote occurring on your graph if that limit is infinite. Let's take a look at some theorems here. So if we have a real number a, and we have the limit of g of x going to 0, and the limit of f of x going to a where a is not 0, then the following statements can be made. So if a is positive, greater than 0, and g of x is going to 0 through positive values, then the limit of f of x over g of x will be what? Let's figure that out. So according to our limit laws, we should be able to take the limit of this quotient and turn it into the quotient of the limits. So the limit of the numerator, the limit of f, we said was going to a, and the limit of g, we said, was going to 0. Now in this example, we're assuming that a is positive, and we're assuming that g is going to 0 through positive values as well. So look at this little fraction that I've created over here. If we have a positive constant that is not 0 over something that is 0 and going through positives as well, then this is going to go to positive infinity. And we would say that we have a vertical asymptote at this x value c that's making this graph shoot to infinity. So a constant over 0 is going to go to infinity. Okay? Now if we take the same limit, but this time we're letting a be positive again, so the limit of f, the limit of this numerator, is going to a, and that's a positive constant, and the limit of g this time is going to 0 still, but this time through negative values. What would this limit be? So again, we have a positive divided by a negative, so that's going to stay negative, and a constant divided by 0 blows up. So this is going to go to infinity. If we have a being negative, then this numerator is going to go to a negative constant on top. And if g is going to 0 on the bottom through positive values, then again we have a negative divided by a positive, which is going to stay negative, and a constant divided by 0 blows up, and in this case would be going to negative infinity. And finally, if a is a negative constant and g is going to 0 through negative values, now we have a negative over a negative, which becomes positive, and a constant divided by 0 blows up, so this is going to go to positive infinity. So to summarize here, basically what we have is that a number divided by 0 is going to go to either positive or negative infinity depending on the signs of your numerator and your denominator. Okay? And this is true whether you're taking a two-sided limit or a limit from the right or a limit from the left. Also, it is still the case that if the limit of the top is 0 and the limit of the bottom is 0, then we have one of those indeterminate forms, 0 over 0. So if we get an indeterminate form, we will have to be a little bit more creative and try another technique to help us simplify that limit. A couple more properties. This time let's let c and l be any real numbers, and let f and g be functions such that f goes to infinity and g goes to l. So what would be the sum or difference of the limit as x approaches c of f of x plus or minus g of x? Well, our limit laws again would apply here. The limit of a sum and difference is the sum or difference of the limits. So the limit of just the f is infinity, and the limit of just the g is that L. So what do you think is going to happen if we have something that's going to infinity plus or minus a constant L? Well, that's going to stay infinite. Okay, so if one of these is infinite, then the sum or difference is going to stay infinite. How about if we're talking about a product? So what happens if we take the limit of a product where the limit of the f is infinite and the limit of g is a constant L? So what's infinity times a constant? Still infinity. And if that L is positive, this will be positive infinity. If that L is negative, then this will be negative infinity. And then finally, a quotient. If your limit of your numerator g is going to that constant L and the limit of your denominator f is going to that infinity, what happens to something that's a constant over something really, really big? So think about that for a moment. Suppose we have any number like the number 1 and we divide it by something really, really, really big, like 1,000,000. Well, that's really, really, really small, right? The fraction becomes really, really, really small. So a constant over something big gets small and goes to 0. So to summarize, a constant or a number over something infinite is going to go to 0 in the limit. And what we said on the previous page is that a constant divided by something small, like 0, goes infinite. So it's kind of a reciprocal relationship here. So a number over something big gets small, a number over something small gets big. All of these properties hold for one-sided limits and for functions for which the limit of f of x as x approaches c is negative infinity as well. So it doesn't just have to be for positive infinities. All right, let's go ahead and find some limits. So here we have the limit as x approaches 2 from the right-hand side of x plus 3 over x minus 2. Now, to do these limits, you're going to do that number 1 rule that we always follow with limits, and that is to try plugging in and see what you get. If you get one of those indeterminate forms, then we'll have to be a little bit more careful. If we don't get one of those indeterminate forms, then we'll know our answer right away. So if I plug in 2 plus 3 would be 5. And if I plug in 2 on the bottom, 2 minus 2 is 0. So this fits this sort of formula that I have right here. We have a constant on the top and we have a 0 on the bottom. So this is going to go to something infinite. The question is it positive infinity or negative infinity? And you have to be a little bit more careful about plugging things in to figure out which sign it's going to be. Now if I plug in 2 from the right-hand side, remember that 2 from the right-hand side means you're looking at x is slightly bigger than 2. For example, you could be letting x be 2.01, something a little bit bigger than 2. So imagine plugging in 2.01 on top. Well, obviously that's going to still be close to 5, and 5 is positive. On the bottom, however, 2.01 minus 2 is going to be positive 0.01. So what we say is that since we're coming from the right-hand side of 2, we are getting closer to 0, but we're getting closer to 0 through positive values, because we're always plugging in something just slightly bigger than 2 and subtracting 2 from that. So that's always going to be a positive answer back again. So a positive divided by a positive means this is going to positive infinity. Now, if you wanted to verify this, you could just pull up your calculator and you could look at a graph. So if you go to y equals, you could type in x plus 3 in the top. Make sure you're using parentheses around that numerator, and then we're going to divide by parentheses x minus 2 in the bottom. And then I'm just going to do a standard window, so zoom standard, and we see that we have this asymptote showing up. And we're coming from the right-hand side of 2, so that would be this right branch over here. And as my car drives up the curve, I'm driving up towards infinity. So that graphical depiction does verify our conclusion that we had. So you can always graph these as well, but I try to do them as much as I can algebraically so that I don't have to pull up this calculator every time. So now let's take a look at the next example and do something very similar. So again, we want the limit as we approach 2 from the right-hand side, which means the x's that we're going to be plugging in here are numbers slightly bigger than 2, like 2.01, for example, or 2.001. Whatever you want, as long as it's slightly larger than 2. If I plug in my 2 minus 5 would be negative 3 on the top. 2 minus 2 would be 0 on the bottom. So obviously the top is negative. It's the bottom that we're interested in. We know that this is going to go to some kind of an infinity because a constant divided by 0 does become infinite. It's just a matter of whether this is plus or minus infinity. So the top we know is negative. It's the bottom that we need to worry about. And if I'm plugging in 2.01 right here, that's going to give me 0.01, which is positive on the bottom. So these are going to be values in the denominator that are always positive, but getting closer and closer to 0. So we have a negative divided by a positive, which is going to stay negative. So my answer for this limit would be minus infinity. Okay, let's try another one. If I plug in 3 into this limit, 1 minus 3 is negative 2. And 3 minus 3 is 0. So we have a constant over 0, so this is going to be infinite. The numerator is already negative. It's the bottom we have to look at. Now this time we're looking at a left-hand limit from the left side of 3. So what would be an example of a number that's slightly to the left of 3? Well, that would be something like 2.99, something just a little bit less than 3. If you were to plug in 2.99 and subtract 3 from that, that's going to give you negative 0.01 for an answer. So that means these zeros are actually zeros through negative values. So we have a negative divided by a negative means this is going to end up being positive. All right, let's try the next one here. The limit as we approach 3 from the left-hand side of 2x minus 1 over x minus 3. If we plug in our 3, 2 times 3 is 6, 6 minus 1 is 5, and on the bottom 3 minus 3 is 0. So the top is positive, the bottom we need to look at more closely. If we're coming from the left side of 3, something smaller than 3, that might be something like 2.99, and if I plug in 2.99 and subtract 3 from it, that's going to give me a negative answer. So a constant divided by 0 goes to infinity, but a positive divided by a negative means this is going to be negative infinity. Okay, if we go to the next one and plug in right away, 2 plus 1 is 3, and on the bottom 2 squared is 4, 8 times 2 is 16, so we're going to get 16 minus 16 is 0. Now notice that denominator is a quadratic, so potentially it could factor, and I usually find it easier to go ahead and put it in its factored form when I'm trying to figure out my signs. So let's go ahead and factor this. I'm going to need two numbers that multiply to 12 and add or subtract to negative 8. Well, that's got to be a minus 6 and a minus 2. So if we take a look at our signs, we know this is going to infinity because it's a constant over 0, but in terms of the signs, I know the numerator is positive, positive 3. In the bottom, I need to be plugging in something slightly bigger than 2, like 2.01. So if you were to plug in a 2.01 right here and subtract 6 from that, that's going to be negative. If I were to plug in 2.1 minus 2, that's going to be positive. And when you multiply a negative times a positive, that stays negative. So that's how I use those factors to figure out my signs. A positive divided by a negative stays negative, so my limit is minus infinity. Okay, on the next one, this is a two-sided limit. If I plug in 2 right away, 2 cubed is 8. 8 minus 8 is going to give me 0, and 2 minus 2 on the bottom is also going to give me 0. So this is one of those indeterminate forms. So if you have a 0 on the top and on the bottom, you can't conclude anything yet. You have to be a little bit more clever. So what we're going to do is use some of our strategies, and what you want to notice is that this numerator, x cubed minus 8, is a difference of 2 cubes. That means it factors. So if I factor it, one of the factors is the cube root of x cubed, which would just be x, minus the cube root of 8, which is just 2. Use the same sign in this first factor that you saw in the original problem. This was a difference, so my first factor should be a difference. The second factor comes from this x squared, this 2 squared, which is 4, and that's always positive, and the middle term is x times 2, and the sign of that middle term should be the opposite sign of this first factor. So if this is minus, this needs to be plus. Now, you need to memorize how to factor a sum or difference of cubes. Trying to come up with this on your own through guess and check is going to be very tedious, so it's much simpler to just memorize the pattern. 2 terms in the first factor, 3 terms in the second factor. Now, luckily for us, these x minus 2's cancel out, so the limit is going to be the same as the limit of whatever x squared plus 2x plus 4 gives me. And that I can plug 2 into and get a value for. 2 squared is 4, plus 2 times 2 is 4, plus another 4 gives me 3 4s, or 12. So this limit is 12. Probably not something you would have guessed from initially knowing that this was an indeterminate form. Okay, let's take a look at the next one here. I want the limit of this function here as I approach 5 from the right-hand side. Now, I see a lot of quadratics here, so you can go ahead and plug in right away, or you can factor right away. It's kind of up to you. If you plug in right away, you're going to get 5 squared, which is 25. 25 minus 9 is 16. And on the bottom, 5 squared is 25. 3 times 5 is 15. 25 minus 15 is 10. 10 minus 10 is 0. So this is going to be going to some kind of infinity. It's a question of whether it's positive or negative. Now, deciding the signs on this, I think, is a little bit easier to do if you're looking at the factored form. So I'm going to go ahead and rewrite this in its factored form. The top is that difference of squares, x plus 3x minus 3. And the bottom is going to be, I need an x and an x, and a 5 and a 2. I need the 5 to be negative and the 2 to be plus to get a negative 3 in the middle. Now, none of these factors match or cancel out, so we don't have that issue going on. But remember, when we plugged in initially, this was like a 16 over a 0. Now, the 16 is obviously going to be positive. The bottom, however, we need to know the sign of. So when I plug in, what I'm going to be plugging in is some x value from the right side of 5, which means slightly bigger than 5, so something like 5.01. So if you were to plug in 5.01 on the top, or excuse me, in this first factor, 5.01 minus a 5 is positive, positive 0.01. If I were to plug in 5.01 into the second factor, 5.01 plus 2 is 7.01, which is also positive. And a positive times a positive means this is going to 0 through positive values. And that means we have a constant over 0, which is going to infinity, and a positive over a positive stays positive. So let's do this same exact problem, but this time we're going to do it through negative values, or excuse me, left-hand limit of 5, not necessarily negative values. So I'm going to recopy my factored form here, and I am going to still be getting that 16 over that 0 if I just plug in my 5, but the difference is going to be possibly the signs in the bottom. So if we're coming from the left side of 5, that's something smaller than 5, like maybe 4.99. So if you were to plug that in right here, 4.99 minus a 5 is negative 0.01, so that's negative. If you plug in 4.99 right here and add 2 to that, that stays positive. So we have a negative times a positive, which means this is going to 0 through negative values. 16 is obviously positive, so a positive divided by a negative goes to minus infinity. Only the denominator where that 0 is do you really have to worry about the signs. The top number, the constant on the top, you'll already know what sign it is. So you don't need to waste your time trying to plug in 4.99 into the two numerators. You already know that that's going to 16, and 16 is positive already. It's just the 0 that you have to worry about, whether it's getting close to 0 from the right or from the left. So just worry about your denominators. Okay, let's take a look. Now this is that same fraction again, so same factors, x minus 3, x plus 3, and x minus 5, and x plus 2. And this time I'm approaching negative 2 from the left-hand side. So let's just see what we would get if we had plugged in negative 2 from the very beginning. Negative 2 squared becomes positive 4. 4 minus 9 is negative 5. So we know the numerator is negative. The bottom is going to have to be a 0 because we know that x plus 2 is one of the factors. And if you plug in negative 2 into that factor, that's going to go to 0. Or if you did plug it in just to see, you'd get 4 plus 6, which is 10, and 10 minus 10 is 0. So this is going to a negative 5 over a 0, which we know is something infinite. But we need to look at our signs to see what that 0 is doing. So negative 2 from the left-hand side, think about a number line. If you're coming from the left-hand side of negative 2, what would that represent? Be careful with your negatives here. Something slightly to the left of negative 2 would be something like negative 2.1. So if you plug in negative 2.1 and subtract 5 from that, that's definitely negative. And negative 2.1 plus 2 is going to be negative 0.1, so that's also negative. So the denominator is a minus times a minus, which is a plus. So overall, we have a negative divided by a positive, which stays negative. Okay, so now if we take a look at the other side of negative 2 and come from the right side, that means we're going to be picking a number slightly to the right of negative 2, so this direction. So that would be something like negative 1.99. So if we plug in negative 1.99 on the bottom and subtract 5 from that, that's going to stay negative. And then negative 1.99 plus a 2 becomes positive. So that 0 in the bottom is a negative times a positive, which is negative, and that numerator was still that constant negative 5. So a negative divided by a negative becomes positive, and this is going to infinity. Alright, let's try the limit as we approach 2 from the right-hand side of x squared minus 4 over x minus 2. If I plug in 2 right away, 2 squared is 4, 4 minus 4 is 0, 2 minus 2 is 0. So this is one of those indeterminate forms. So I'm going to use one of my tricks again, and that is to factor that numerator into x minus 2, x plus 2. The x minus 2's cancel out. So we're left with the limit as x approaches 2 from the right-hand side of x plus 2. And if I plug in 2 into that, 2 plus 2 is going to be 4. And it doesn't matter that it's a right-hand limit here, because we're not going to 0 or something like that where it's going to matter what sign we are. This would be something slowly getting closer and closer to 2, but what we were taking the limit of was a nice linear function. So direct substitution will work for us. So our final answer here, just 4. Okay, now the next two are a little bit trickier. If we plug in 0 right away, then this is going to be acting like 1 over 0, and that 0 is going to be positive because when you square anything, that becomes positive. So 1 over something really small through positives gets really big. In other words, it blows up to positive infinity. If I look at 1 over 0 for this second one, this time the 0 is going through negatives because I'm not squaring it. So 1 over 0 through negatives also blows up, but it's going to go down to a minus infinity because we have a positive divided by a negative. So what happens if we take a positive infinity minus a negative infinity? Well, double negative cancels out, and what do you think positive infinity plus positive infinity is? Well, that's still infinity, still positive infinity. An infinite number, a really, really, really large number, plus another really, really, really large number is going to stay really, really, really large. So this is going to be infinity. Now what happens if we plug in 0 from the right-hand side? So if I plug in 0 from the right-hand side and I square that, it's going to stay 0 and it's going to stay positive because of the square. And 1 over 0 through positives goes to positive infinity. If I plug in 0 through positives on this second fraction, then this is also going to be positive infinity. But here's the tricky part. We want to subtract these. So some people might think, oh, well, infinity minus infinity, doesn't that cancel out and give you 0? Not necessarily, because infinity is not a number. It's really a symbol that represents the fact that this keeps getting bigger and bigger and bigger. So you can't really subtract two infinities from each other and get a 0. So this infinity minus infinity is actually another thing that we call an indeterminate form. It's another type of an indeterminate form, which means a limit could possibly exist still. You just have to be a little bit more creative to figure it out. So here's the strategy that we're going to use. Let me clear some space here. When you get infinity minus infinity like this, you can't just claim that it's 0. It might not be. And what we're going to do to really prove what this limit actually is we're going to notice that since we're dealing with two fractions that have different denominators, one thing that might help here would be to get a common denominator. So let's see if we can do that. See if we can rewrite this function in a different way that will have a limit instead of leaving us with an indeterminate form. So what would my common denominator need to be? Well, it's got to be x squared. So if I have 1 over x squared already, that one doesn't need to change. But if I want to change this second fraction into a denominator of x squared, that requires multiplying by x's on top and bottom. Now if I get this simplified, now that there is a single denominator here that's the same, I can combine these and make the numerator just become 1 minus x. Now once we have our common denominator, let's go ahead and try plugging in our 0 now and see if it makes a difference. So if we plug in 0 into the top, we're going to get 1 minus 0, or just a 1. If we plug in 0 in the bottom, we're going to get 0. Now the top is obviously positive, it's a positive 1. Is the 0 going through 0 through positives or negatives? Because of this square in the denominator, this is going to have to go through positives, because whatever you plug in, no matter whether it was positive x's or negative x's, it would get squared away to a positive anyway. So we have ended up with a constant divided by 0, which blows up, and since it was a positive divided by a positive, this goes to positive infinity. So in this problem, even though we started with infinity minus infinity, on this particular example only, that ended up becoming an infinite limit through positive infinity. That isn't always the case, though. Sometimes you might actually end up with a finite number for your limit answer. Okay, let's try another example here. This one has that greatest integer function in it. So I'm going to use my limit laws here and take the limit of the numerator, which is a difference, and take the limit of each piece and subtract, and I'm going to take the limit of my denominator. So let's see if we can figure out what some of these limits are. Let's find the limit of just this greatest integer function first. And that, you need to remember, is one of those step functions that has a width of 1 and jumps up by 1 unit each time. And we're looking at this from the left side of 2. So from the left side of 2 means we're on this little step right here, which is at a height of 1. So the limit from the left side of 2 of the greatest integer function is equal to 1. If I plug in 2 into just x, that's going to give me that 2 back again. And if I plug in 2 into the bottom, that's going to give me 2 minus 2. So in the numerator, we're getting 1 minus 2, which is negative 1. And on the bottom, we're getting a 0. Is that 0 through positives or negatives? Well, it depends on which side of 2 we're coming from. If we're coming from the left side of 2, we need to be slightly less than 2. So that might be an x value like 1.99. If you were to plug in 1.99 into that bottom, 2 minus 1.99 is positive. So what we get is a constant over 0, which is infinite, and a negative divided by a positive stays negative. So this is going to negative infinity. Okay? On the next one here, we have the limit, right-hand limit, as we approach 2, of 3 over x squared minus 5x plus 6 minus 1 over x minus 2. So if I plug in 2 right away, the top of this first fraction is going to stay 3. 2 squared is 4. 4 minus 10 is negative 6. Negative 6 plus 6 would be 0. So this is going to be going to some kind of infinity. Could be positive or a negative infinity. We'll have to explore our signs a little bit more. On the bottom, we have 1 over 2 minus 2, which is also going to 0. So this is going to some kind of infinity as well. And we're subtracting these two things. So this is one of those indeterminate forms where we need to be a little bit more careful. And just like in the other example we did like this, since we have a fraction minus a fraction, the best way to deal with this is to get that common denominator and try to combine these two fractions using that common denominator. So let me make some space. And before we jump into what our common denominator should be, you probably want to factor this first denominator to see what it has within it. And we would need an x minus 2 and an x minus 3 to get that minus 5 in the middle. So both fractions here have an x minus 2, but this first one also has an x minus 3 in it. So we're going to need to have in our common denominator both x minus 2 and x minus 3. Now the first fraction already had that, so its numerator stays 3. When we subtract the second numerator, it has just the x minus 2, so I would need to multiply the top and the bottom by x minus 3. And notice I'm leaving it in parentheses because we want to subtract all of that, and we're going to need to distribute this negative in the next step. So let's go ahead and do that. Let's distribute our negative. We're just trying to clean up this fraction as much as we possibly can before we try plugging in our 2 again. So we're going to get 3 minus x plus 3, which becomes the limit as x approaches 2 from the right-hand side of 6 minus x over x minus 2 times x minus 3. Now once you've gotten your common denominator and you've kind of cleaned it up as much as you can, now is the time to plug in again. So we're going to plug in 2. 6 minus 2 would be 4, and that's obviously positive. On the bottom, we're going to plug in 2 down here, and that's going to give me a 0 times a negative 1. So this is obviously going to 0. Now we need to look at that 0 a little bit more carefully to see what sign it's going to be. So if we're coming from the right-hand side of 2, that would be something a little bit bigger than 2, like 2.1 or 2.01. And if I plug in 2.01 and I subtract 2 from that, that's going to stay positive. If I plug in 2.1 and subtract 3 from that, that's going to be negative. So positive times a negative means this is going to 0 through negative values. So our final limit is infinity, because we have a constant over 0, and then a positive divided by a negative stays negative. Alright, same exact problem, but this time we're going through the limit from the left side of 2. So all the work that we did up here would be exactly the same. I didn't use the fact that this was a right-hand limit until I actually investigated my signs in this very last step. So in other words, once I get my common denominator and clean this all up, it's still going to look like what we got before. 6 minus x over x minus 2 times x minus 3. That part won't change. The only part that's going to change is what I plug in and what signs I'm going to get. So if we plug in 2 on the top, we're still going to get that 4, which is obviously positive. But this time we're going to plug in a 2 that's slightly less because we're coming from the left side. So something like 1.99. If we plug that into this first factor, 1.99 minus 2 is negative. 1.99 minus 3 is negative. And we're going to get that 0 on the bottom because 2 minus 2 is 0, but it's going to be 0 through positives because a minus times a minus becomes plus. So this is going to infinity, and because it's plus over plus, it's going to positive infinity. Okay, our last question, true or false? If p of x is a polynomial, then the function given by f of x equals p of x over x minus 1 has a vertical asymptote at x equals 1. So think about that for a moment. Is this function going to have a vertical asymptote at x equals 1 because we have that x minus 1 factor in our denominator? Well, normally you might think yes, because you have asymptotes typically when your denominator is 0, which does happen at x equals 1 here. But what's the one exception to that rule? The one exception is if you, instead of having a vertical asymptote, you have a hole, which would require that x minus 1 is a factor of this polynomial p of x. So if you had an x minus 1 on top and an x minus 1 on the bottom, remember those would cancel out and you would no longer have a vertical asymptote. Instead, you would have a hole at x equals 1. So is this true or false? Well, it could be false if x minus 1 is a factor of p of x. Now, what's another way of saying that x minus 1 is a factor of p of x? Well, if x minus 1 is a factor of p of x, that means if you were to plug in 1 into p of x, you should be getting 0. That's another way of saying that x minus 1 is a factor. So either way you want to write it, this is going to be false if x minus 1 is a factor of your polynomial, or if you plug in 1 and you get 0. In other words, you'd get that 0 over 0 indeterminate form. Otherwise, if these aren't the case, then you would have a vertical asymptote left over. Alright, that concludes our lecture on infinite limits. Good luck!